But yeah, let's get started. So this chat is called Demystifying Proxies. So the world of smart contract development is pretty complex, and there are a whole bunch of different standards out there. And so hopefully this talk will be a good way to learn those different standards, some of the ways that they came about, and then hopefully also to be a good reference point. I'm not too sure the experience of the crowd. This is an intermediate to advanced talk. So if you've never written a line of Solidity before, you might be a little lost. But if you've poked around with Solidity and are familiar with the syntax and its programming, then my hope here is that I can teach you a little bit about how the EVM works, how proxies are possible. So yeah, let's get started. A little bit about me. Oh, that says agenda. I'll fix that. This is just about me. So I'm a smart contract dev for a crypto project called Bulla Network. We're based here out of Denver, Colorado. We are a on-chain accounting, invoicing, and commerce protocol. I also teach a Solidity deep dive meetup here in Denver as well. We like to meet in person, but we also have streams. So my streams can be found on my YouTube channel. I try to stream them for anyone who can't meet up with us in person, but you're welcome to join those online. We do those every month. There's also I've embedded links into these slides, so you can go through and check any of these after the fact. But there's a link to our meetup if you're local. And there's a link to my project, and I have my GitHub, my Twitter, and my streams here. And then the talk repo is here as well. But yeah, that's a little bit about me. So what we're going to talk about is proxies, like I said. First off, if you're familiar with Ethereum smart contracts, the intent of smart contracts is that they were non-upgradable. Is that originally the idea was that you would have a fixed piece of code that exists forever. That therefore, if the code is safe, it's safe. No one can change it. It's permissionless. It exists in this decentralized blockchain, and anyone can interact with it. But there's this standard for this upgradability standard called Proxy, the Proxy standard that came out of Ethereum development in the last few years, which allows you to upgrade smart contracts. So exactly what you asked, Rob, in chat. If there was ever an issue with your smart contracts, or heaven forbid you write software with a bug, which we all do and is inevitable, there's actually a way to mitigate some of that damage by upgrading the logic. So you wouldn't be able to do things like recover tokens or kind of undone any harm that was or money that was lost, but you could upgrade your logic in your smart contracts to make sure that those kind of exploits couldn't happen again. It's kind of a hotly debated topic of upgradable versus non-upgradable software. I fall in the middle. I think some things should be upgradable. I think we all write bugs in our code as software developers. We have to avoid the hubris of thinking that we write perfect code just because we stare at it for 6 months. People are really clever, and they're very clever when there's $1 million in a contract and they can find a way to break it, right? So I think I see both sides to upgradability, and I think that depends on your use case, whether or not you'll need it. But the agenda for today is some required knowledge of what you'll need to know about the EVM, the Ethereum virtual machine. That is the runtime environment that the Ethereum and EVM-based blockchains run on. So Ethereum mainnet, Polygon, Gnosis Chain, Avalanche are a couple of the most popular EVM-based blockchains. An example of a non-EVM blockchain would be like Solana. So that wouldn't apply to this talk because these are EVM patterns and Solidity patterns specifically. I'm going to talk about the required knowledge and then a few different proxy types, and we'll get to go through that here. So feel free to drop any questions in the chat, and I will do my best to stop along the way. If they're really in-depth questions, we'll answer them at the end, just for the sake of everyone's time here. So here are these prerequisites that we're going to talk about. So we're going to talk about transactions, how transactions work and how they're structured. Delegate call, how delegate call works on the EVM. How the EVM smart contracts handle, how Ethereum smart contracts handle storage, with what's called like storage slots. So how values in storage have pointers and how they're referenced and loaded and saved. And then fallback functions, and that's a feature of Solidity. And if you combine all four of those, I guess kind of difficult to understand topics, then you will be able to have the knowledge to understand how a basic proxy works. So if we nail these four, then the different types of proxies and why they were why these standards were created for the different types of proxies will kind of be able to fall into place, because you'll have this underlying prerequisite knowledge. But first of all, let's talk about transactions real quick. So data on the internet, just to start from super broad perspective, is just bytes, right? It's just bytes going over the wire. It's 0x, it's 0x, well, it's bits actually. So it's zeros and ones, right? It's on, off. You combine those zeros and x's together. The step above is a byte, right? Which is just the 0 to 16 representation of those bits. So this is what we see in Ethereum. This is where you get all those fun little like 0x names on like Twitter and things like that, is because 0x is a almost like a delimiter that means that something's going to be in hexadecimal format. So every transaction that happens on Ethereum is hexadecimal. Every address on Ethereum is hexadecimal. That's just how data works on Ethereum, right? So data in general on the internet is like streams of bytes, right? And there's different formats for how to interpret those bytes. Ethereum has its own standard of how to interpret bytes that's been kind of really developed by Solidity, and it has this sort of like function selector and call data structure to it. So every transaction has two sections. Bytes 0 through 4 are going to be the function selector, and then bytes 4 through n, so like as however much data you need to send in one transaction, is going to be postpended to the function selector. So the function selector is the leftmost 4 bytes of the Kachak hash of the function signature. So like what all that means is that when you write a function in Solidity like total supply, what your Solidity code will compile down to is a executable part of your program that is delineated by this like function signature, right? So in Solidity, the standard is you hash the string of whatever your function name is, and then the last 4 bytes of that that's your function selector, right? And so that's how the EVM determines like, okay, when Colin calls transfer to, right? I, as a human, see plain English transfer to. That's how I write my code. That's how I interpret other people's code. Is like, okay, this is a token. I'm going to transfer to this. How the EVM interprets that is it hashes that value, takes the 4 bytes, and that's the selector. And for reference, I put this little table here that this is all the parts that make up a transaction. I believe this is actually missing 2 things since EIP 1559 for those who are familiar. But usually it's just a from address. So I send a transaction to another address with a value and a data field, right? That can be empty or have any of this here in blue. It could have any kind of call data here. I specify a gas limit of like how much I think that transaction should cost, and a gas price. And usually this is all handled by your wallet if you've ever used MetaMask, things like that. So just to really solidify this, I want to show you a transaction. I want to show you 2 transactions. So this is a transaction just from my test wallet, right? Like if you're familiar with Etherscan, what I did is I just sent my friend some Ether, right? So I just specified, hey, send my friend 0.001 Ether. It's from me. It's to this other wallet, and it has this value, right? As we can see, there's no input data, but input data is what makes up a transaction, and theoretically, I could do that. So here's this other transaction where I put input data, right? And you'll see this anywhere. So this input data can be anything you want, right? So if I view this input data as a UTF-8 string, because you can, UTF is an encoding for how hexadecimal bytes appear as like English characters, right? Or maybe other languages too. But I can put any data I want in this input field, right? So Ethereum in general has this way to structure transactions where you send transactions from address A to address B that's cryptographically secure. And you can include any kind of data you want in there. And what will happen when the to address receives that call, the to address will be invoked, right? So it will be invoked and it can do whatever it wants. And so how contracts work is you send a transaction to a contract with specific input data. The receiving contract is invoked. It grabs your input data, decodes it based on however you write your program, and then does something else on the blockchain. And so, like, just to make sure that we're really clear about how the EVM works, think the EVM is really, it is as simple. Let me just pull up my chat here again. It is as simple as that. So that's how transactions work at a base level. And some folks aren't familiar with that. I definitely started developing smart contracts without the knowledge of that, because Solidity kind of takes all that craziness away from you. But you need to know this to understand how proxies really work. So, moving on. I guess I explained some of this already, but I just wanted to show it. So, like I said, a transaction will execute any kind of code on the receiver. So what it does, what's called a call opcode. So it calls the receiver, right? Here's an example of some low-level Solidity code. So this is a let's see, this is a like precompiled a piece of code from a ERC20 token. And so this is the last step. This is what's called, if you're interested, it's called the intermediate pipeline, the YOL pipeline for Solidity. So it compiles it for your Solidity code into what's called YOL, and then it will compile it down in a bytecode that can run on the EVM. And so this is like a really low level representation of your Solidity code for like an ERC20 token. But so all call data gets interpreted by what's called the hub. And the hub just looks like this. If you're familiar with programming, it's just a switch case, right? So what it does is it shifts your call data right 224 bits, which the Ethereum blockchain works in 32 byte chunks. 32 bytes is 256 bits. 256 bits minus 224 bits is going to be 32 bits. 32 bits is 4 bytes. So all that to say is that like it will figure out, it'll grab that the red part of the code here. It'll grab this function selector, and then it will do like a switch case against that function selector to see, okay, if it's the hash of function name, forward the execution of this program to where you've defined how to run the name function. If it's the approve function, go here. If it's the total supply function, go here. And so this is how all smart contracts compiled in Solidity works, is that it has this thing called a hub. And so it's just a big switch case that handles calls, intercepted calls. So it just takes, like I said, it takes the first 4 bytes of the function and jumps to the program execution to that function. And so here's something that's interesting. If it doesn't match this is a switch case, right? Sometimes, for those who are familiar, there's like usually like switch case default, and that's where we get into fallback functions. So if it doesn't match, right? So if there's no matching selector here, it'll trigger what's called a fallback function. a fallback function is always it's always defined by the user. My slides are a little backwards here. Oh wait, I guess they're not backwards. I think I'm missing the, apologies, some bumps in the road here, but I guess I don't have the slides for what a fallback function is. Oh yeah, I do. Here we go. I don't know why it's over here. Anyway, but this should be the next slide. I'll fix that. So you could specify what's called a fallback function to catch any non-matching function selector, right? So this is what it looks like in Solidity code, right? You can specify a fallback function to catch any non-matching selector. If the first 4 bytes of the call data doesn't match any function specified in the hub, the fallback is called. So basically, it's a way to say like, hey, I don't know how to interpret this call data. I haven't written any specific function for it, but there's I just want you to handle this transaction, right? So like there's 2 flavors of fallback. There's a fallback and a receive function. There's like a fallback function will be executed if there's data in the transaction. If there's not data and there's like a value, the receive function will be executed. So these are these 2 flavors, right? So I could say that like if someone, so this is my, this is my cool token here, right? It's an ERC20. If I say that someone just like sends ether to this, then I'm going to mint them like 100 ether, right? So if I send like 0.01 ETH, notice that like that doesn't match any function on here. So it's going to trigger receive. It's going to trigger this receive function, right? Or if I try to call like a function called, I don't know, hello world or foo or bar or whatever on this address, there's no matching function called foo or bar. So it's going to trigger the fallback function because it's like, it just doesn't match. So it's going to like dump the program execution to this fallback function. So all that to say is like really think about the fallback function as a way of, as like a specific instruction set for executing code when I guess like, let me think. It's like an arbitrary execution mechanism. So like it could just arbitrarily execute regardless of whatever call data it's received. And so that's going to be pretty important for our like proxy recipe that we're starting to build here. So okay, perfect. Yeah, we got a question here. So wait, receive is fallback. Receive is fallback if payment was sent, but fallback is the default. There's a little chart that actually really helps that I'll include in this talk and in the repo as well. But so I've included a yeah. So here's the repo here, right? So here's my token. So this is the normal cool token, and this is the cool token with fallback. I've also included the UL representations of those two. So if you go into the UL folder, I have cool token and cool token with fallback. That is, these are deployed. And if you open this in with the Solidity language in VS Code, you want to go to, I'll make a note here, Codementor here. So this is the deployed code, right? So you'll see here's kind of that switch case against the selector, right? So this is how a normal hub works, right? It will do a switch case against all the possible function names that it knows of as like an ERC20 token. So you'll see, like the transfer function, different things like that, right? And then you'll notice at the end, if the program is executed this far, then it will revert with this error here. But if you contrast that with the cool token with fallback, let me open this in Solidity. Let me go to the hub. These contracts are pretty dense. Here we go. They're not meant to be read by humans, really. So this is our cool token with fallback, right? So for example, what this will do is this will say, this has both a fallback and a receive function. So this means that if the call data size is 0, go to the receive function. So meaning if there's no call data, go to the receive function. Else, if there's call value, then revert. Otherwise, if there is just like normal data, then go to the fallback function. And that's because I specified in my cool token with fallback that fallback is not payable, right? So it looks to see, hey, is this just like a contract? Is this just like am I just receiving ETH, or am I receiving data? And if I'm receiving ETH and data, then I'll revert. But if we put payable in here, this wouldn't be there. It would just be, it would say, hey, if there's no call data, then go to the receive function and stop execution. Otherwise, go to the fallback function. But receive is another fallback function. Is that correct? Yeah, they're two flavors of the same thing. Exactly. Okay. Cool. Rob said, I think that makes sense in the chat. Perfect. Okay. So next we're going to move on to understanding storage slots real quick. So smart contract storage is an array ranging from 0 to 2 to the 256 minus 1. So like if you're familiar with arrays in computer science, right, they have indices. So I could store things in an array. So I could say like I have an array called states, right? Like say the array is called like United States. And then, at index 0, the first state that I store is like Alabama, right? And then the next at index 1 is Arkansas, things like that. So this is how storage works on smart contracts as well. I'm talking permanent storage, not memory storage or anything like that. Not the memory that just sort of exists in the cycle of one transaction, but the permanent storage that's written to the blockchain. So this is pretty easy to visualize because it's just a visual top to bottom position in the contract indicates the index based on Solidity storage packing rules. So storage slots are 0 to 256 long, like it's an array, right? But the width of the array is 32 bytes each. So the EVM works on 32 byte slots because it was efficient for the hashing algorithms. So like some other VMs work on like more like 4 byte like memory, like registers, different things like that. The architecture of the EVM works on 32 byte slots. It's very simple, and whether you're in the stack or in memory is just a volatile array, but yeah, the stack and the storage system works on 32 bytes. So we can see here that you can review these storage packing rules because we'll see here some of this doesn't really starts to not make sense in a second, right? Like we have a UN256 here, which makes sense. It's a variable 1, so that would be slot 0. Bytes 32, variable 2, that's also slot 0, right? These are two things that take up 32 bytes. But Solidity is pretty smart. Even if you have two different values here, it will actually say, okay, you went 128, you went 128. Well, when you add those values up, that adds up to 256, which still fits into the same 32 byte slot. So what it will do is it will actually pack those and together so that you only use one storage slot. And the reason why is because storage is expensive. That's the most expensive thing you can do in your Solidity program is store things in long-term storage. So what it will do is it will try to reduce the amount of storage that happens, and so it will what's called pack those values together. So there's rules that are defined in the Solidity spec of like what packing does. So it'll try to pack as much as it can into one slot, and if it's greater than 32 bytes or 256 bits, then it will just jump to the next slot. So that's important for you to realize too. So let's see, how does that affect me as a coder when writing contracts? So for you as a coder writing contracts, you want to make sure that your variables in long-term storage are as small as need be, right? So, for example, if you're storing a timestamp, your timestamp does not like a timestamp in seconds. Your timestamp does not have to. It doesn't have to take up the full. It doesn't have to be a full uint 256. You can actually use a smaller variable called like a uint 40, and that will take you up to the year 21,000 or something like that. So plenty of time for your users to create timestamps. So like that's an example too. And if you can pack it with other variables like an address, which is a uint 160 underlying, then you can save your users about maybe like 25,000 gas, which depending on the gas cost is going to be maybe like $1 or $2 every single time someone runs your program. Yeah, exactly. So it reduces gas fees by using less size. That's it. Perfect. But just like what I want you to visualize is like when you as a developer write variable 1 and variable 2, really like put yourself in the shoes of the EVM and think, when I write function, set var and I pass a new var, right? When I write variable 1 equals new var, I'm thinking take value X and set it at slot 0, right? So that's what my instruction set is: store whatever is in call data here in slot 0. This will also be important in a bit too. Just like a quick aside here, with assembly, you can read and write to any slot, which is really neat. This is DIY because Solidity normally puts a lot of guardrails on you to make sure that you're writing in a place that's safe. So like this is slot 0, this is slot 1, right? But when I use this assembly block here, I could say, this is a getter. I could say use the S store, right? So I'm saying write new var at storage slot 1. Here, this get var 2 is I'm doing what's called an S load command at storage slot 1 as well. So it will load from storage slot 1 and assign it to this variable here. I can also do things like store things at a random storage slot really far down my tree, right? So, or really far down my array. So the point is with assembly, you can completely DIY a contract storage. Oh yeah, this is just for you to come and look at later if you'd like. I know we need to pick up the speed, but so notice in the packing rules how structs follow the same rule as storage. So if you ever wanted to go into the diamond standard, you'll see why this is important, right? So if I defined a struct, here, the way that these variables are packed together follow the exact same way that a contract's variables are packed together. So we can actually represent the storage values of our smart contract in a struct. And so we could say that, so like in this example, right, like slot is a member of struct, meaning that like I can actually set a pointer for my storage layout. So normally, like in the example above, I have like slot 0 and slot 1 that store my variables. But here, if I say that like my random slot, I actually want my smart contract storage to start very far down the array, then I can specify that myself. And so combining these techniques, you can create reusable storage read writes to a custom slot in storage. And the reason why that gets important in the future is because with proxies, you deal with this idea of storage conflicts because you've stepped outside of the safety of Solidity, and so you could accidentally overwrite variables, and that's maybe for a little bit more of an advanced deep dive. But I got another question that says, in that random example, can you store to a slot not defined by var? So yeah, in that random example here, so what I could do is I could actually have set var take in 2 parameters. I could have it take in a slot number and then the value I want to store. And then essentially I've exposed a way via a function to arbitrarily store in any slot. And I believe does that answer your question? Cool, sweet. Okay, next is delegate call. This is the last prerequisite that we'll need to know to really understand and get our hands dirty with proxies. I said in the beginning, and I also said on the description of this talk that we went in here trying to learn about proxies, but ended up learning about all of these low-level EVM things that will not only make us a better developer, but make us write proxies safer. So the last thing that we need to know is about delegate call. Delegate call is like a special op code. And so I want to show you what delegate call does is imagine this box on the left is a contract at a fixed address. And this box on the right is a contract at a fixed address. What delegate call will do is it will call to this code and allow this code to modify this contract storage. So normally, when I in Ethereum make a call from one contract to another, I go from contract A, and the call sends to contract B, and the contract B can only execute and store variables and store values on its own contract. But delegate call is special. It's saying it delegates the authority of writing to a contract storage to whatever the call receiver is, right? One way that I like to imagine it is if I had 2 contracts here, like a piece of paper, right? Like with the code printed out, and this contract is making a delegate call to this contract. I just imagine with a piece of scissors, snipping out the whole function from the contract that's being called and executing it here. That's basically what it does. Is it says, hey, take this snippet of code and execute it here. And on a technical level, that's not quite what it does. It more just it does something different. But that is absolutely a sufficient mental model because delegate call was really tricky for me to wrap my head around, and I think it's tricky for a lot of people. We'll look at a quick example here. So delegate call allows for a contract to modify state. So message sent, also too, what I mentioned, not only does it allow it to modify state, but also message sender, message data, and message value are kept the same between the different, between the call. For example, I have 2 contracts here, indecisive partner and assertive partner, right? So there is this, at storage slot 0, there's a string called dinner location, right? And so indecisive partner has a function called where should we go to dinner, right? And what it will do is it can do a delegate call. Remember, this is me building up my own little function selector here, right? So I take the dinner plans function selector as a string, and I hash it, and then I take the rightmost 4 bytes, and then I can use that to delegate call. So what I'm saying is, and I'll show you how this works. I made some arrows here. So if I call where should we go to dinner, what it will do is this next line that executes is it will go to the partner and it will do a delegate call to the partner with the function dinner plans. So what happens to in dinner plans, we see that this storage variable, dinner location, so slot 0, is modified with the string Illegal Pete's. Illegal Pete's is a taco place here in Denver. It's pretty good. I would be the assertive partner in this situation. But it will normally, if I call dinner plans on the assertive partner just in a normal call, it would set its own dinner location, right? But since we're doing a delegate call, and we can imagine these functions saying this function instruction set saying write this string to slot 0, what it will actually do is it will snip that code and execute it here, saying write the string illegal piece to slot 0. Does that make sense, right? That there's like this, this code executes, but it executes in the context of this function. I'm going to allow that to like simmer just for like 10 seconds and like let me know if you have any questions, but that's delegate call. Yeah, exactly. Yeah. So Rob said, wow, that's interesting. You don't have to set the partner return value to dinner location. Yeah, totally true. Right. So, you know, in a normal context, like a safe context, like normally in programming, if I had two different like functions, right, I rely on the return value of that function to tell me what to do in this context, right? But actually, it's almost like I'm forwarding my memory pointers to another function so that that function can modify and then pass the execution back. So it's like a really strange paradigm. It works well with blockchain, but it can be insecure because you have to trust the contract you're delegating to, or else that delegate contract could write to any slot in storage. So that's the caveat, right? And if this isn't quite making sense yet, I would just keep imagining these two. Well, first of all, I would open this up after this talk and just keep imagining this instruction set as, okay, I have this string slot 0. This instruction set says write this string to slot 0. And so if I just execute it in this context, it's going to write this string to slot 0. But the context was here. So whatever slot 0 is here now at this point will be whatever the string is that this contract determined. Okay, and there's my fallback in the wrong place. Okay, yes. How does the bool success get set with no return in the assertive part? Oh, yes. So that's like more of an implementation detail of how call and delegate call work in Solidity itself, right? So if I go to my partner's code here, right, I see partner. So like address is in Solidity has a member is like has the members call and delegate call. So for example, like I see in my little documentation thing here that call, they have the same function selector, but you can call arbitrarily a function by passing it bytes, and it returns bool and the return data. So it issues a low level call. So specifically, and then delegate call does the same. You pass it bytes and it returns a bool, which is a success, and then any return data. And you have to parse that manually. So like normally, if I actually had, so if I told Solidity that this partner was a assertive partner, and then if I asked for dinner plans, right? If dinner plans ever like reverted, if dinner plans ever reverted, then this whole function call would revert because Solidity has like checks the success of each call, versus if I kind of like do like a YOLO call here and do like either like a low level delegate or a low level call, I actually have to check that success, and I have to also decode that return data myself. Versus Solidity, if you wrap it in like a function definition, it will handle the parsing of that for you. So yeah, this is just like an implementation detail. Okay, so here we go. Done all that learning. Hope your minds are buzzing, right? But now we have enough ingredients to put together our basic proxy recipe, where we would have like one contract that has like a fallback function, which can forward all calls to a contract that handles the logic, and then have all the storage exist at another contract. So like where we kind of like when we add all those caveats of the EVM and of Solidity together, we can combine fallback, storage slots, and transactions to create a contract where storage is kept at a single address. The logic is determined by another address. And if you don't like that logic anymore, you can just, upgrade the logic address, and then it will, but the storage will stay in one place. So you can upgrade your logic of your contract, and then, but you don't have to upgrade like your front end with your addresses, or you don't have to index, you don't have to migrate token balances. Token balances can stay at one address, but the logic is upgradable. So we'll talk about like a few different, like what that could look like a minimal proxy. So the first type is a minimal proxy. So to create a proxy, we would need to load in the call data, right? So imagine loading in the call data, and then we're going to do a delegate call. We're going to pass all that call data to whatever our logic contract is. It says, so the receiving contract, what's called the proxy contract, receives all the call data. It loads it into memory. It asks the logic contract what to do with that call data, and then modifies, and then asks that, allows that contract to be a delegate call to modify its own internal storage. So the minimal proxy is the smallest version of that. The bytecode is literally this, right? So normally smart contracts are huge on Ethereum. They're really expensive to deploy. If you're familiar with OpenZeppelin, this is the clones implementation. But this is EIP 1167 minimal proxy, and this BE, that would just be, you just replace that with the address of the logic contract. So this is non-upgradable. There's no code in here to upgrade, but all these opcodes, they will load the call data in, and then it'll forward it along, and then handle if it fails or if it succeeds. So it's super cheap to deploy. Like imagine I have a really logically complex contract. I can just deploy one instance and then have a whole bunch of little minimal proxies that get their own storage. So this is great for where logic is complex and needs to be reused. So for example, Gnosis Safe. Let me open up an example here, but oh no, they I guess they moved the Gnosis Safe proxy. What if we go to proxy not found, safe contracts? Okay, here we go. We'll find it. Contracts, proxies. What was it? What was the name of the contract again? It was, yeah, safe proxy. Looks like they renamed it. I'll make sure to update that. But here's the safe proxy, right? It's really small, and they use assembly, right? So maybe to give you all an example of this, let's walk through this code real quick. I'm going to copy this into my IDE so that we can see these four elements really kind of combined together. So let me remove some of these comments here. So what I could do with this, okay, so here we go. Let's get our feet wet here. So this is how the safe proxy works. We deploy a safe proxy and we specify an address that's called a singleton. So the singleton is like the logic contract, right? And it sets the singleton as the contract. What it will then do is the only other function it has is it has a fallback function notice. And this fallback function is payable too. So it'll handle both calls with data and calls with Ether, or both, right? So like it will kind of handle every single call that goes to this contract once it's been deployed. We'll just go arbitrarily to this contract here. So what it does is it just, this assembly means it loads up that singleton address. Then what it does is, oh, I've got some text here from my block explorer. Then it will, you can ignore this. This is like a Gnosis Safe specific thing. It will copy the call data into memory, and then it will perform a delegate call to that singleton address. And then if the success is 0, meaning it fails, it will revert. Otherwise, if the success is not 0, so like success 1 equals true, then it will return the return data. So it's just almost acting as like a gatekeeper for all the calls that pass to this contract. So every call will go to this contract. It will be forwarded on to the singleton and then return any data. Is that making sense? Do we have any questions there before I move along? This might take a few slides to kind of grasp. Okay, makes sense. Good. Cool. And there's a great deep dive here on exactly what this bytecode does if you want to become like a Solidity bytecode wizard. So the next type is going to be transparent proxies. So this is a different EIP standard, and what it does is it specifies 2 contracts. There's a proxy contract and an admin contract, and there's a specific interface for upgradability. So when you're looking maybe at like building a smart contract system or some sort of upgradable contracts, you really have 2 options. You have like transparent proxies, UUPS, and beacon proxies, and these are the 3 we're going to talk about here real quick. So it's easy to upgrade, but you must deploy an admin contract to manage the proxy. So I'll show you real quick what the TLDR is, the show me the code version, right? So this is a transparent upgradable proxy, right? What it does is it has some ways to upgrade to a new implementation address if you're an admin. It has a way to change the admin address to a new admin if you're the admin. It actually has a way to return the implementation address if you'd like, and it has a way to return the admin address if you'd like as well. Specifically, everything kind of happens in this modifier, if admin, right? So it says that like if I am a wallet that sends a transaction to this upgradable proxy, this transparent upgradable proxy, if I send a transaction and I'm the admin, then it will just execute as normal, right? But if I'm not the admin, it will delegate it to the fallback. So it'll perform a fallback call to a fallback receiver, so like a logic and an implementation contract. So that's kind of how it works, right? Is that everyone else gets to just everyone else's call is forwarded straight to the logic contract, but admin calls are handled by the proxy contract itself. So you can imagine it like I just like imagine it kind of like maybe there's like a big hole in the ground, but there's like scaffolding on the sides, right? And if you're an admin, the scaffolding catches you. If you're not an admin, you just fall straight down to the implementation contract. So that's one type of proxy. And next is UUPS. So it's the universal upgradable proxy standard, and it's the ERC 1822 is kind of where it first came out. So it's just a really simple standard for defining a proxy contract and a base logic contract, and all calls are forwarded. So it doesn't matter if you're an admin. There's no admin contract to actually manage these calls. There's also no fixed interface. So there's no admin contractor functions, and calls are cheaper too, because it doesn't have to determine if you're an admin on whether or not to load it. It just passes all the function calls to whatever your implementation address is. This is kind of how it works. Is what it does. This is the 1822 example. The Open Zeppelin standard does a little bit different now. But if you remember what I said about slots, is a slot is just a slot indice is just a very large number. Well, it could be from 0 to a very, very large number. So what it did is it just hashed together this some string to create some random, very, very, very large number. And then that is the slot where the implementation address is actually going to be stored. So if my contract is a Proxyable logic contract, it's going to have an update code address. In Open Zeppelin standard, you'll see this as authorize upgrade. And so authorize upgrade just allows you to upgrade the contract itself. You don't have to be an admin. You just have to have the right authorization privileges. And so what it also does is it defines some introspection as well. So it has this function Proxyable UUID that's defined by the EIP spec. And when you call that Proxyable UUID function, it should return the standard implementation storage slot. So the EIP determines where the logic address should be stored, and it should be here. So you can perform some introspection, right? So like if I was to update the code address to a new address, the EVM doesn't know anything about this new address. It's just an address. But what it can do is it can wrap that new address in like an interface, and it will call that Proxyable UUID function. If this reverts or fails or returns 0, right? Then it knows that it's not compatible, right? So it helps you not brick your upgrade patterns by doing a non-standard by having like a non-standard UU or UUPS contract that you're trying to upgrade to, right? Like for example, right? Like if you were trying to upgrade your if you're trying to upgrade the engine in your car and you put in the engine of a truck, your car would be broken because you didn't use the engine of a car, right? It's the same thing. So it just performs what's called introspection on the new address. Let's see. There was one other thing I wanted to mention about this. Oh yeah, it's the fact that I think the UUPS standard is really interesting because you don't have to think and manage or manage security, right? For the long term. So for example, like what I could do is I could write a smart contract ecosystem that is upgradable with UUPS. But I like to write a V1. V1 has some bugs or some math issues, so then I do a V2. I figure out how to make it more gas efficient, so then I make a V3. And then things have been like going well in my protocol for 2 years. And then what I can do is I can upgrade that to a V4, but maybe put like a hard revert on any authorized upgrade call. So essentially, I've taken the power out of my hands as a developer or as a DAO or as like someone with private keys to control how this smart contract works in the long term. So it's a great way to sort of have to be able to like move quick and pivot on the fly when you're creating these smart contract systems initially, and then either pass off the upgrade functionality to the community, which should be dangerous, or you pass off the upgrade functionality, or you just renounce it almost. And this is a way to kind of keep smart contracts safe, right? Where it's like you can upgrade it to a time and then just determine it non-upgradable after a certain time. So that's definitely a benefit. The last, we're coming up on time here, but the last proxy that I wanted to mention is a beacon proxy, right? So like, so beacon proxy is just a slightly different pattern, right? So it's for when you need a bunch of different proxies, proxy addresses, but you want to upgrade the implementation logic of all of them, right? So if you think normally, if each of these proxies was a UUPS and you created some new logic, you would have to go and upgrade every single one, and it'd be really tedious. But with a beacon proxy, you could say, hey, this proxy's logic points to this beacon, and then the beacon determines actually where the logic contract is. And so it will do a delegate call to another delegate call to the beacon, from the beacon to the logic contract. And so like, for example, like where this might come in handy is, if we look at our first example of a minimal proxy in Gnosis safe, right? This is a hard-coded address, right? So how could we say, everyone gets their own Gnosis safe, but we also trust Gnosis to upgrade to version 1.4 or 1.5 in the future, and I just want to be automatically upgraded, what you could do is you could say that, instead of just like one address, it points to a beacon. And that's another way of doing things. Just some proxy survival tips to wrap up. You'll see around poking around smart contracts, you'll see these the phrases like master copy, singleton, implementation, beacon. Just think of all those things as the address where the logic contract resides. So like the proxy contract receives calls, the master copy, singleton, implementation, beacon, all that other jargon. It just means the logic contract that determines what happens to that code, that determines how storage read writes are updated. Another thing is you can't use constructors in upgradable proxy code. Open Zeppelin goes over this and why, because constructors is like it's made for deployment to be run at deployment time only, and there's really sort of no notion of deployment time with a proxy. You want to handle it all by your by explicit functions, and Open Zeppelin walks you through this in a way. This is great. If you're writing proxy contracts, always use the Open Zeppelin hard hat plugin when developing with proxies. It will really you just need to use it. It helps you avoid slot conflicts where like maybe my storage in one code said, write to slot 0, and my total supply was at slot 0 and balance of was at slot 1. But maybe in the next upgrade, you flip those and you accidentally put balance of at slot 0. And so now your new logic contract is going to just start breaking your storage. It helps you identify those issues before you actually go to deployment. And then also you need to protect your upgrade functions with like only owner calls or other types of protections, like wrap it with a multi-sig or something like that. Here are 2 articles which are great. This is kind of the entry point to. Let me pull this down here. This is like the entry point to working with Open Zeppelin's upgradable contracts. This is here in their documentation. It's called Using Upgrades. This talks about how you need to refactor your code to not use constructors, and how like inheritance works and storage gaps, things like that. And then this is probably one of the best series that I've seen on here we go, on writing upgradable smart contracts. It's this whole tab here, Solidity, Proxy Pattern, and Upgradable Smart Contracts. It talks about the problems, how storage collisions are avoided, how we got to the proxy standard, how things like fallback work, like I talked about, and then some of the different standards. Another fascinating standard, if you think that this is like very interesting to you and you want to use proxies, is the diamond standard. The diamond standard kind of takes proxies another step forward and creates safe wrappers for all the storage variables, creates safe wrappers for how function execution is delegated and upgraded. But that looks like the end. I think we're 2 minutes over time here. So if you have to leave, that's just fine. But yep, that's the talk on kind of beginning to demystify proxies. Feel free to reach out to me at any time. I love walking people through code and teaching folks. I'm here on Codementor as well. So please reach out to me on my Codementor profile. Follow me on Twitter if you'd like. I don't post much, but yeah, no, please stay in touch. I think the more that we write smart contracts together and answer these tough questions of what are these standards, how do these things work under the hood, the better developers will be and the safer the space will be. So yeah, thanks so much. I'll be around for another like 10 minutes to do like Q&A and other answers, but thanks everyone for coming. Looks like we have another question from Rob. It says, say you have a contract that users deposited ETH into and you had upgraded it, how would you deal with storage and transferring the ETH to a new contract? So the cool thing is you would never say, maybe I didn't make this clear in the talk, but when you deploy like a proxy contract, what you would call the proxy contract, that is the code that your users interact with at all times. It has the token balances, it has the allowances, it's the address that people use consistently. It's the addresses that your front end points to as well. When you deploy the logic contract, that logic contract, that address is only used in the terms of the proxy contract itself. So you'd never send tokens to the logic contract itself. Yes, exactly. So the proxy contract holds all the ETH. So when you upgrade from the logic contract from contract 1 to contract 2 to contract 3, right? It's just the logic of how the runtime execution is handled. But the balances stay at that fixed address. Yeah, sure. And Anwar, you're welcome. And Donna, you're welcome. Omar, you're welcome. Tony the Coder, you're welcome. Great to have you all. Yeah, please shoot for it, Rob. Go for it. I'm going to just fix my fallback slide while we're at it. And this is it. Perfect. Okay, so the question here is, say I write a contract that needs to interact with SushiSwap or Trader Joe or another contract. In my test environment, those third-party contracts don't exist. So how can I test my code? Yeah, exactly. So, sorry, I'm just pulling back up my stream code here. Yeah, so there are two things that you can do. Depends on the tool you're using, but both tools support them. So what you can do is you sounds like in this case you want to fork mainnet. So you would first take all the contract addresses that you want to interact with on SushiSwap or Trader Joe, and then what you're going to do is you're going to put them into what's like a constants file or somewhere like at the top of your test code. And then when you run your tests, if you're using Hardhat or Foundry, I don't know about Truffle, but when you run your tests, you're going to specify, I'll use Ganache. Okay. Well, look up how to do forking in Ganache, because with Hardhat, all you have to do is specify, if you're using the command line, you say like -- fork URL or like RPC URL, and then you just pass it like an RPC URL. And then what it will do is it will take the state of the current blockchain, and it will run all the calls in your that happen. It'll like identify all the calls in your code, and then it'll actually ask the RPC node to simulate that and then return that, right? It's kind of like cloning their contracts and interacting with them, but like say you start your tests at block 7,000,008, right? Then and you specify a fork URL, it will go to 7 million. Like your local test, like the blockchain will just keep doing its thing after you start running a test. But like you will have a branched version of the state, and you can do things like, you can spoof admin data. You can pretend to be another address. There's a whole bunch of different things that you can do when you are forking the blockchain. But so can I just clone their contracts and interact with them? Basically, yeah, correct. Yeah. Okay, so it's even better. It's like snapshots the blockchain and uses its data. Yeah, that's exactly it. So it'll run your calls against the current blockchain state or the current blockchain state at the fork. That's a way to do it. If you wanted it to be really fast, then you could copy the contracts that you need into your local repo and then deploy them. But that gets really complex because usually the deployment steps are complex for these protocols. And then you need to have balances, all these things. But I would need to specify the contracts to fork, though, right? Not because it's just going to fork every contract that exists. Well, so you could actually treat it as if it does fork every contract that exists. It doesn't do that. It just asks for a simulation at a certain block. But the code is all public, right? So like if I had the public code that exists, it will run that simulation at a certain block number and then just return whatever the smart contract returned to you. So I would just look up like Ganache forking. And if you wanted a hand with that, reach out to me on Codementor and we can walk through. I can help you walk through that if that's getting like convoluted. Yeah, you're welcome.